So, what we have seen earlier class is to look at a mechanism called catalytic mechanism. Okay. So, we have seen few examples before. Okay. One which is a simple electron transfer reaction. Next is a two-step reaction with one adsorbed intermediate. We also seen three-step reaction with two adsorbed intermediates. We have seen two other type of reactions. One is adsorption along with electron transfer, which we call as EAR. Another is what we call as catalytic mechanism, where you have anion coming in and it needs adsorbed species and a vacant species sitting next to each other for the reaction to proceed, or for that step to proceed. Okay. And in these examples we saw that it can give rise to current versus potential curve, where current increases and then decreases with respect to potential, and this causes a negative impedance. Now, I want to take up an example where we do not assume it is Langmuir isotherm. Okay. Langmuir isotherm model is easy to work with, okay. But when we look at the situation, actually these adsorbed species are charged species and they will have an interaction, they will typically repel each other. Okay. So, if you think about it, if one location you have M adsorbed, it is likely that another adsorbed species or another atom will lose an electron if it is far away from this. If it is right next to this, it may not lose an electron that easily. Okay. We are able to manage with Langmuir isotherm model to simulate lot of the observed results, but we should also know how to handle the cases where the rate constant depends on the surface coverage, and in some situations it is necessary to use that. Okay. One example is in fuel cells, PEM fuel cells. You have a reaction where hydrogen gets oxidized, oxygen gets reduced, and in case you have a hydrogen stream coming in, it may have trace amount of carbon monoxide, and CO poisoning can affect this reaction. And in those cases, the rate constants or some of the rate constants depend on the surface coverage of the species, and that is necessary to incorporate to describe what we see. Before we go to that example, I want to start with a simpler example, and with that we will complete the set of examples we see for RMA and then describe few challenges that one faces when you actually try to optimize the kinetic parameters and fit the model to this data. Okay. First, I want to start with this example. We have seen this before. It is a first case where we looked at adsorbed intermediate. You have metal losing an electron and become metal plus adsorbed, and metal plus adsorbed loses another electron, and this is not the correct thing. It should say metal 2 plus solution. Okay. So, you have this metal can lose an atom, become adsorbed species. Next step, it loses one more electron and goes into the solution, M2 plus solution. Therefore, it will become a vacant site again. Now, the first reaction, we know the rate of the first reaction is given by K1 1 minus theta. We know the rate of the second reaction is given by K2 theta, and theta is the fractional surface coverage of M plus adsorbed species. This is the only adsorbed species that we are looking at, the remaining is the vacant metal, and we know gamma d theta by dt equal to this. We have seen this before. We can write the current from the first step, it is K1 1 minus theta, from the second step the rate is K2 theta, and both of them give electron. Therefore, we have to add them, multiply by Faraday constant to get the total current out of the overall reaction. This is the Faraday current from this. Now, we had assumed earlier that the K1, K2 etc. are dependent on potential, and otherwise they are not dependent on surface coverage or anything. That is the reason we can apply Langmuir isotherm model. Now, Fromkin isotherm, the interaction between the adsorbed species cannot be neglected. Adsorbed species may repel next species or it may attract. Typically, it will repel, it has a parameter called G. If that G is positive, it means the adsorbed species will repel each other. If it is negative, it means it will attract each other, that will facilitate the formation of that species, and if it is 0, it becomes Langmuir isotherm. There are actually many other isotherm models. Another model is called Temkin isotherm. Temkin isotherm assumes there is no interaction between the species, but the sites that are available on the surface, they are not uniform, they are not identical. Some sites are more favorable for adsorption, some sites are less favorable for adsorption. Therefore, when new adsorbed species forms, it is going to first form in the location where it is more favorable, and when that is completely filled up with adsorbed species, it will go to the next level where it is little harder, but it can form again. With more effort it can form again. So, that means the rate constant will change once the surface coverage is significant, meaning it has filled up all the EC areas, it will become harder. So, it will become slower. So, theta here will affect the rate constant value. Actually, all that they describe is how the equilibrium constant in a reversible reaction, if I take K1 K minus 1, Temkin isotherm or Fromkin isotherm basically describe the equilibrium constant, they do not describe the rate constant. Rate constant is for kinetics, equilibrium constant is a thermodynamic value. However, if you take the rate constant to be a function of theta and with the parameter beta 1, I will describe what that is shortly. If you give a rate constant like this, then the equilibrium constant also will come in this form. Okay. Right now, we are taking the reverse reaction is negligible because we are operating in a region where it is very positive potential and forward reaction is significant. If we take K minus 1 to be 0, K minus 1 to be like this, and if we take the ratio of K1 and K minus 1 to get the equilibrium constant, then you would find that the form of the equilibrium constant is also going to be like this. At a given DC potential, this is of course not here, it is K minus 1 here. It is going to exponentially depend on theta, exponentially depend on potential, depending on the value of beta 1, beta minus 1, etc. Okay. Since we know it is going to depend on theta, we know beta equilibrium cannot be 0. It is going to depend on ADC, B1 and B minus 1. In fact, they will have opposite signs. B1 is going to be positive, B minus 1 is going to be negative. So, B1 minus B minus 1 will not be 0. So, all that the isotherms describe is that it is going to be exponentially dependent on theta, exponentially dependent on potential because it is for an electrochemical reaction. The form of Fromkin equation and Temkin equation will be same, meaning you can have a rate constant dependent on the surface coverage because the species interact. You can have the rate constant dependent on surface coverage because the sites are not equal, but both of them will give rise to the same expression at the end. So, you cannot really distinguish based on simple evaluation of a rate constant or equilibrium constant as a function of theta. You cannot say this is Fromkin isotherm or this is Temkin isotherm, they will look similar. If you have other way of finding and identifying the sites are different, then you can say it is Temkin. If you have some way of proving sites are equal, but the moment I put one species I am not able to put another species next to that by some other technique, then you can say yes, Fromkin isotherm is operational here. So, as an analogy, sometimes I give this example. Okay. If you go to a canteen, let us say all the seats are equal. If some are occupied, if you know them, they are friends, you are likely to go next to them. If you do not know them or you know them, you do not like them, you are likely to go to the place away from them. This is one type of description. Okay. So, when somebody sees from outside, they do not know the individuals, they just see that okay, if it is occupied, the person is going to be far away. If it is empty, they are going to sit randomly in some place. this will represent Fromkin isotherm. Okay. Another example, you go to a place, you know all of them, they are equally friends. However, let us just say there are only few of them there and the seats are not equal, meaning some seats have better view, some seats have poorer view. You are likely to go to the seat which has a better view first. Anybody who comes in will choose that. When that is full, they will go to the next one. When pretty much everything is full, they will go to the one which has a very poor view. So, that is going to be an example for Temkin isotherm. When somebody looks from outside, all that they will see is here, of course, if you know which site is what, then somebody who looks from outside will know that people always preferentially go to that site. But if they only have data on it is occupied, this is how it looks like, if it is not occupied, this is how it looks like, then they will not be able to see a difference between the rate constant or the preferential occupation in Temkin isotherm case and in Fromkin isotherm case. Because in our visualization or in the example I mentioned, we already think we know which site is better, which site is poorer, or we can identify the sites. But if you are not able to identify, all that you have is it is going to be fast, it is going to be slow, or another way to say that is, if it is empty, view is good, you are likely to go and sit there. If it is full, you will think, should I really go in or should I wait and then go later, let it get empty and then I will go. So, that means the rate becomes slower. If it is fully empty, whether it is Temkin or Fromkin, you will see same behavior. You go quickly occupy some place, you may occupy a special place or you may occupy a random place, but you do not have to think and make a decision. If it is partially occupied, you will have to think and make a decision. Okay. Coming back to this, here we are going to assume that the species are going to repel each other, meaning you have M plus adsorbed formed in one location, you are not likely to have another. I mean, it is possible that it will form, but it is not very easy. Its rate constant is going to be slower for that. We get the following description: K1 and K2 are dependent on potential as well as on theta, and G is positive, that describes its repulsion. And the reason this may happen is because of del G, freenet of formation of this species. Okay. It is linearly varying with theta. The first rate, the first equation, first step, okay, that is going to be formation of theta. So, we expect when theta is more, K1 will decrease. Therefore, we should say when theta increases, K1 decreases, which means beta 1 has to be negative. G is positive. I want K1 to decrease when theta increases, that is going to happen when beta 1 is negative. K2 on the other hand removes M plus adsorbed. So, if you have lot of M plus adsorbed in this, fractional surface coverage is high. Since they repel each other, it is easier for them to go out. Does it make sense? It is like this. Now, you are going there, you do not like each other, anyway you eat lunch, you want to finish and go off quickly. And if it is more or less full, you do not like each other, you are thinking whether to go in or not when you are outside. So, the first step it is going to be slower if it is full, second step is going to be faster if it is full. Therefore, beta 2 is going to be positive because K2 increases when theta is high. No, it is a Fromkin parameter. If G is negative, it basically means its attraction. When G is 0, it simplifies to Langmuir isotherm. See, Fromkin isotherm does not tell us anything about K1 and K minus 1 or K2, it just tells K1 equilibrium, K2 equilibrium. We just propose that rate constant can be this form because this will lead to Fromkin isotherm, but you might be able to come up with another expression for individual rate constants K1, K minus 1, K2, K minus 2, such that the equilibrium constant is still exponentially dependent on theta. We are just not using those things, this is a simpler way of doing it. So, normally what we do here, we get these equations, we first write steady state. So, we want to get theta SS, then we will take this equation and take this equation, mass balance and charge balance, linearize them, we will get an expression for d theta by dE, we will get an expression for IAC as a function of EAC and it will also have d theta by dE. Then we will rearrange it so that we can get EAC by IAC or IAC by EAC, does not matter, and we will get an expression for Faradaic impedance or Faradaic admittance. This is the procedure that we have followed so far. So, first step is to get the steady state value, second step is to write these two equations and then linearize them, truncate, rearrange, get the values. So, steady state values I would like to get. What do I do here? I take this equation, set this to 0. Set this to 0 because potential is a constant, it is a DC. And theta should be written as, of course, I have not done this correctly, I will delete it, this term multiplied by 1 minus theta SS, this term multiplied by theta SS, and if I subtract them, that is going to go to 0. This equation we cannot solve it analytically, we will have to use numerical method to solve it. When you use numerical method, this is easy to solve though, because theta SS lies between 0 to 1. So, you can take Excel, this assumes, of course, I have already given you k 1 0, g, beta 1, b 1, k 2 0, beta 2, b 2, all those values are given to us. Then for a given DC potential EDC, you will have to find theta SS. So, if you vary the value of theta SS from 0 to 1, you will find it is crossing 0 at some location. So, you can find the value, except that you can't write an expression here and say that theta SS equal to k 1 DC by k 1 DC plus k 2 DC, something similar you have done before. You can't just write an analytical expression and say that this is the solution, but it is possible to do it using pretty much any software or programming language which you can use for plotting or which you can use for programming. It is possible to do it quickly. For example, if you take MATLAB, just take theta SS for going from 0 in steps of 0.001 till 1, you will see where it crosses 0 and that is where it is going to be. That is a very simple way of doing it. You can use an optimization program and get that, that is also okay. I do not think really theta value of 6 or 10 decimals accuracy is necessary. You probably want to know it in 2 decimals, 3 decimals accuracy, that is more than enough. So, next is the step where we want to linearize mass balance equation. K 1, earlier we would have taken this and then written k 1 equal to k 1 0 e power b 1 e, and that means k 1 0 e power b 1 e DC multiplied by b 1 e AC. This part we would have taken as 1 plus x square by 2 factorial and so on, and then said roughly this is 1 plus x, that means I will write it as 1 plus b 1 e AC. This part we would have taken and said this I will call it as k 1 DC, because this is a value of k 1 at the DC potential. This we know how to handle it, it is going to give us this part is going to approximately be equal to this. This is a constant anyway. I would like to take this part and linearize it. When we linearize, we are going to write like this, correct. We are going to write it as d theta by d EAC 1 by 2 factorial d square theta by d E square EAC square, and then we are going to neglect those things. Therefore, this is roughly equal to theta SS plus d theta by d EAC. EAC is a small number. What happens to e power beta 1 g theta? So, there is 1 approximately equal to, because I truncated the series. So, after substituting for theta in the truncated form, I can expand this and I can write this as a product of 2 terms. This I can leave it as it is. This I can again expand in Taylor series and truncate it. So, this I would write it as approximation here. So, initially we write theta, expand it, truncate it, then we realize the theta actually comes in exponential form. We had to substitute anything that is small, you can expand in Taylor series and truncate, anything that is large you keep it as it is. Theta SS we do not know whether it is going to be large or small. EAC we assume it is small, it is in our control, we can make it as small as possible or as small as we want, as large as we want. Therefore, we are going to keep that as a small number here. So, k1 I can write it as k10 e power beta 1 g theta ss e power b1 e dc, and then I have 1 plus beta 1 g d theta by dE EAC that comes from the first part here, theta part here, and then 1 plus B1 EAC that comes from the second part, potential part. So, previously I would have just had k10 remaining as it is, e power B1 E gives rise to one term here, 1 plus B1 EAC. Here we have 2 EAC terms, 2 terms each one having an EAC term here. And earlier I would have said, when we used Langmuir isotherm, I would have said k10 e power B1 E dC is the value of k1 at dC. Here the value of k1 at dC is given by the term which I just covered here. So, this I would write it as k1 dC. So, if I apply a small AC, previously it is going to vary around k1 dC, it is going to be around that, and the variation is going to be given by B1 EAC. Here it is going to be little more complex. You would write k1 or k2, I would write it as ki here, ki is going to vary around ki dC, but the variation is given by 1 plus B1 AC EAC multiplied by 1 plus beta 1 or beta 2, whatever that is corresponding one, g d theta by dE EAC. Okay with this? Okay. So, whatever you have done for k1 you can do for k2. Theta is not going to be special, we have seen this before, it is going to be just theta SS plus d theta by dE EAC. So, I would like you to write this equation left hand side, it is going to be similar to what we had done before. Right hand side, it is going to be little more complex. See, when we looked at catalytic mechanism, we found that it is a second order reaction in one of those steps. That means, k1 will give rise to one EAC term, theta will give rise to one EAC term, 1 minus theta will give rise to one EAC term, and when you multiply this you will get up to cubic level, but we are going to anyway truncate at first order. Therefore, we will neglect EAC square, EAC cube. We have to do the same thing here. k1 here gives rise to 2 EAC terms here. So, the product I will get 4 terms in the k1, but I will retain only 3 terms. Right now, I am just keeping them as they are. Theta will give rise to one more EAC minus K2 dc. Thank you. It is 1 minus theta. K2 dc, it is going to be approximated as, sorry, K2 is going to be approximated as K2 dc, B2 EAC is going to be there, 1 plus beta 2 G d theta by d E EAC is going to be there, and this has to be multiplied by theta value, which is going to be theta SS plus d theta by d E EAC. Each term will give rise to constant EAC, EAC square, EAC cube. We are going to neglect EAC square and EAC cube. I would like you to write the constant values, and you will see that they will go to 0. EAC's terms will remain and we will cancel the EAC, but please go through that and rearrange. Maybe one thing that can help you is when you look at 1 minus theta, it is going to be 1 minus theta SS plus d theta by d E EAC within bracket. Keep 1 minus theta as one term and then minus d theta by d E EAC as the second term, because the 1 minus theta SS is a constant term for a given DC, minus d theta by d E is a linear term as far as EAC is concerned. So, sometimes in different notation when people write, they will write 1 minus theta SS as theta V SS, theta vacant site. The first term has to give rise to what I have written here on the top, and the second term to what is written on the bottom, assuming that I have done it correctly. So, if you look at the second term here, it is like A plus B, C plus D, E plus F. This B, D and F are linear functions of EAC. The first number is a constant, theta SS or 1 or 1. So, you are going to have 4 terms when you multiply this, you are going to have 8 terms when you multiply all the 3 terms there. Out of the 8 terms, you will get a constant, you will get EAC, you will get EAC cube, EAC square, neglect or throw away the EAC square and EAC cube terms. Is it okay? Anybody able to get it or okay? So, what I will assume is that if I given some more time, whoever has not got it yet will be able to complete this rearrangement and get this. Once you get this, I have marked 2 terms in red color. These correspond to the DC terms and they will go to 0, because by definition of theta SS, it is K1 DC 1 minus theta SS has to be equal to K2 DC theta SS. That is how we got the steady state values anyway. So, this term will go away, remaining terms are those which are left with EAC. You can cancel out the EACs here, then you can bring d theta by d E terms to the left side, the other terms will remain on the right side, and you can get an expression for d theta by d E equal to something divided by something, and this divided by something will have j omega gamma for sure. So, if necessary, copy these terms and then rearrange it. And one way to check that the expression you got is okay is to set the value of g to 0. If g is set to 0, it has to be Langmuir-Isotherm result, or if you set beta 1 and beta 2 to 0, it should go to Langmuir-Isotherm result. Main point here is it may be lengthy, but it is quite doable. It does not need too much of it is not very difficult in terms of how complex the problem is. It is lengthy, it has many terms, but as long as you have enough time to go through it, verify it, it is actually fairly straightforward. You have to do it slowly and with care, that is all. You get an expression for d theta by d E. This we obtain by linearizing the mass balance equation. You can take the charge balance equation and linearize it here. We use K I as K I DC 1 plus B I EAC, and the next term for the from Kineisotherm. Theta we can substitute as theta SS. This is actually fairly straightforward again. It is again going to be little lengthy, but maybe no, we are short of time. So, what I am going to do is to say that yes, if you spend time you can expand this. you will get a lengthy expression. You can substitute for d theta by d e from the previous case. Before you do that, when you expand it, it is going to give rise to a steady state current and a AC current. So, when you write this in terms of k 1 DC and EAC, theta SS and d theta by d e EAC, you can group all the constant terms together and you can show that they are corresponding to IF DC. Faraday current constant terms will come like this and the EAC terms will come like this, IF AC. We are going to of course neglect EAC square and other higher order terms. So, if you spend enough time, you can rearrange it and take only the AC part, that is going to come as proportional to EAC, and write the ratio of IAC to EAC and call it as Faradaic admittance. Invert it, you will get Faradaic impedance. Point here is, if you write like this, the Faradaic impedance can be modeled using a circuit like this. That it has a resistance, in this case I have written it as R 1 L 1, but we also know that any circuit that is given like this can be modeled by another circuit, or any impedance that is coming from this circuit can be modeled by a circuit like this. So, it is just that here it is easy to relate to the L here, but otherwise it does not mean it has to be a inductance. It may be inductance with negative value for R 1 L 1, it may be a inductance with positive value for R 1 L 1. The reason is you get d theta by d e and everything else is a constant here. D theta by d e is a function of omega. Okay. We have seen this before, d theta by d e comes as a function of omega. It is written like this, but I can divide by the value here in the numerator and denominator. I am going to get k 1 d c, this divide by this entire term, it is going to look like 1 by some resistance plus some other term plus j omega something, it is not resistance, so 1 by some constant. This 3 terms can be written as a resistance in parallel with resistance and inductance, because what do you get here? You get impedance here as R 1 plus j omega L 1, that is going to be the impedance there. This it is going to give you Faradaic impedance. Faradaic impedance for this case, or in general this is going to be the impedance or admittance of this circuit is going to be given by the inverse of this plus inverse of this. Okay. Same form will come here when you look at it here. If I substitute for d theta by d e, ultimately what I would get is one constant here and some d theta by d e multiplied by some constant value parameter here. I can call this as R T inverse, and this is going to be given as 1 by R 1 j omega L, because d theta by d e can be written as 1 by R j omega L. So, in fact I should say all this put together should be the R value, and j omega gamma by this term is going to be the L term. The point is I can write d theta by d e as 1 by some constant plus another constant into j omega, some constant C 1 C 2 j omega. I can call this as R, I can call this as L, does not matter. Ultimately it is one adsorbed intermediate, it is going to give rise to one Maxwell element. It does not matter whether it is Langmuir isotherm or Fromkin isotherm or Temkin isotherm. Of course, the values will differ depending on the rate constant values, but this reaction depending on the values can give rise to a spectrum like this, it can give rise to a spectrum like this in the complex plane plot. And if the values are such that they cancel out each other, it can give rise to only one. That is, if d theta by d is 0, because the numerator is 0, you will not have any impact from this R 1 L 1 parameters. Thing is, it will give rise to one loop at the Faraday because of the Faraday contribution. It can be inductive or capacitive. It may not give rise to this. In fact, when you do experimentally, it may give rise to these two loops, but we may measure only in this frequency range, in which case you will see only one loop. But this cannot give rise to a loop like this, it cannot give rise to a loop like this. So, if it comes like this, you can say it is going to need at least 2 adsorbed intermediate to model this. Although the number of variable parameters, see previously in Langmuir isotherm model K1 0, B1, K2 0, B2, gamma. These are the kinetic parameters that you can vary in order to fit this model to a data set. You have 5 parameters. If you say I think this is following a Fromkin isotherm model, you are adding 3 more parameters, correct. Still it will give rise to only this. So, 5 parameters in Langmuir, 8 parameters in Fromkin for an equation which looks the same. Equation looks the same, mass balance and charge balance equation look the same, it is just the kinetic parameters, the form of the kinetic parameters we are making it dependent on theta, therefore, it gives rise to this. But if I want to get these things correctly, I need to take spectrum at multiple DC potentials to get this, because circuit wise it gives rise to 3 elements. Kinetic parameter wise I am taking either 5 element or 8 elements. If I model with 1 EDC, if I take this, I will get infinite number of solutions. If I assume it is Langmuir isotherm with 2 EDC, I can have some confidence. If I assume it is Fromkin isotherm, I need minimum of 3 DC potentials in order to get the values of these parameters with some confidence. I will come to that later, it is precise way of doing this, but this is to say it is possible to do it. It is lengthy, but it is possible to do it, and at the top level to know how many loops I can get or what kind of mechanism I should use to model a observed spectrum or model spectra, multiple spectra, you need to count the time constants there, and except for the high frequency impedance which comes from double layer, everything else the total number of time constants you get tells you the total number of intermediate species, regardless of whether we say it is following Langmuir isotherm or more complicated isotherm. I think I am going to skip this. You have a lot more complex mechanism that is proposed here and a lot more complex dependency, where one of the rate constant is given in terms of exponential of something. Within that exponent you have 1 minus exponential of something, and that exponent is theta by 1 minus theta. No problem, it is going to take time and few pages, but you can linearize this, and I will show an example of how to linearize this. So, first you take theta as theta SS plus d theta by dE EAC, then keep all the components that are DC in one group, anything with EAC in another group. If it is exponential, keep it as the small number, you can write e power x as 1 plus x, rearrange. It is again exponential, no problem, rearrange. Theta by 1 minus theta, you can expand and rearrange. Okay. Theta by 1 minus theta, right now I am not going to go through, but I want to just show you it is possible to do it, and you can see the description in the file. It is possible to rearrange and get it. So, finally, you can get expression for d theta by dE, you can get an expression for IFAC in terms of EAC, and you can get Faradaic impedance out of this, except that it is going to be very lengthy. So, a lot of times we end up using intermediate variables to describe certain quantities. Okay. Tomorrow what I want to show you is describe some of the challenges faced when you actually have data and you want to get model. Right now, so far what we have seen is, if you are given a model, can we write an expression for Faradaic impedance? Okay. And we also at a superficial level see that if you are given a spectrum or few spectra, we should say this mechanism will never model this, because this has 5 loops and mechanism has only 2 intermediates, or this has 2 loops and my mechanism has only 1 intermediate. So, this can't model, I need to have a mechanism, propose a mechanism with 2 intermediates or 3 intermediates, that much we know. But what else do we have to really do to get this? Okay. So, that we will see tomorrow.
So, the number of loops is equal to the number of intermediates?
Number of loops, high frequency loop you will get because of double layer capacitance and a charge transfer resistance. That means, in a simple electron transfer reaction with no intermediates, you get a curve which looks like this. Anything else in addition to this, how many loops do we have? It does not mean those are the number of intermediates. it means minimum that many intermediates you need. Okay. Let us say I have a data where potential dynamic polarization I versus E shows a curve like this. I take spectrum here, spectrum here, spectrum here. So, and I am going to take it in a finite frequency range, some number, right, maybe 1 millihertz, maybe 1 microhertz. I do not think we have an instrument with 1 microhertz, 10 millihertz, 10 microhertz to 10 kilohertz, 100 kilohertz. It is possible that it shows a spectrum like this at this potential. At this potential, it may show a spectrum like this. This potential, it may show a spectrum like this, or it may show a spectrum like this. It may show a spectrum like this. Then I say, other than this high frequency loop, I have one more loop, either inductive or capacitive. So, I have to look at all the spectra, find the maximum number of loops in those, and then say that many intermediate species is necessary to describe this. It is possible that when you try this mechanism, it may not fit. You can try similar mechanisms with same number of intermediate species and see if it can fit. Does not fit, you may have to go to another more complex mechanism. Minimum number of intermediates that is necessary to describe this can be obtained by looking at the number of loops there. So, it is like saying I have data like this, I know I cannot fit it linearly, but do I need cubic equation, do I need quadratic equation, do I need fourth power? I have to try that and see. Minimum I need quadratic, that visually you can see that and tell, but here you can tell minimum what you need is dependent on the number of loops. If I have a data like this, I cannot do a quadratic, that much I can tell. It may actually be sinusoidal, that is a different story, but in this range I have taken data, it looks like this. I want to model with something that can do this. I have data points 1, 2, 3, 4, 5, 6 data points. It may actually not fit with the cubic, you might need a fourth order, fifth order, but at least cubic is something you should try. Spending our time on linear equation and quadratic equation is a waste of time. It is not going to be dependent on the algorithm we use or initial points we choose, it is never going to fit. Cubic is something where you should spend time, because it has one minimum and one maximum. You know quadratic can represent this, cubic can give you cubic will give you 3 roots, real roots, imaginary, that is a different story. If it differentiate, it is going to give me a quadratic equation, that means it is going to show me 2 zeros, that means I can model one minimum, one maximum, it is a possibility. I should try with the cubic equation. If it does not work, I should see if my algorithm is good. If I am convinced I had done my best, I am not able to fit with cubic, I have to go to fourth order. Likewise, you can choose minimum number of adsorbed intermediates by looking at all the spectra, and then with the same number of adsorbed intermediate you may have multiple mechanisms. There are infinite number of mechanisms one can propose. You propose few reasonable, whatever appears to be reasonable based on whatever evidence you have from other information. For example, if it is ion going to Fe going to Fe3 plus, I will propose Fe2 plus and Fe3 plus as intermediates, because these are stable. Fe1 plus is not known to be a stable intermediate. So, if I am going to come up with 2 intermediates, it is going to be 2 plus and 3 plus, not 1 plus and 2 plus or 1 plus and 3 plus. This information comes from outside, not from the impedance spectrum, because I know something about this system. If it is going to be titanium, I am going to say 3 plus and 4 plus. So, just by looking at the spectrum, I cannot tell everything about this. I have to have some information about the system. Okay, we will stop here today.